Okay, I think they've joined. 2014 bench.
Sir, we can start, sir. We can start.
Yeah. So I think you are able to see the screen. Yesterday we were talking about the uh, torque generation synchronous motor because of the magnetic field created by the stator windings, which is a three-phase rotating magnetic field, which rotates, the magnetic field rotates at ns, called synchronous speed. Please know the image, correct? It is a magnetic flux because the voltage is increasing, decreasing with respect to time axis. With respect to time, as time goes, you can see that each magnetic voltage is varying. This is the magnetic flux we are talking, each phase. That is not constant, it is a sinusoidal varying 180-degree apart. Because of that, there is a resultant magnetic based on the all three at any given instant. That's what we talked yesterday. Because of that, the rotor is attracted. Once it get locked, yesterday we talked that once the rotor also has north and south pole, the stator rotating magnetic field also has a north and south pole. That's what we talked yesterday at given instant. This is the north pole of the stator winding. This is the south pole of this one. You can see that this red color hatched one is the stator on which there are three-phase coil, which we are supplying RGB three-phase voltage. Because at given one instant, this is the resultant, this one, which is called stator field, right? Which we call FS. Similarly, in the rotor, we are given a DC voltage because of the north and south pole is created. You can see that north pole is here, correct? This is the south pole, this is the north pole. And the axis is given like this. This is the stator axis, this is resultant field of the stator. Rotor, this is the stator. Since there are two magnetic fields are acting with some angle, correct, which is mentioned as alpha. This is mentioned as this angle between the stator magnetic field and the rotor magnetic field is called as alpha. Then, because of now we see that there are two magnets. One is a south pole. This is stator south pole. This is the rotor south pole. And you can see that they are opposite pole. Let me clear the screen, then you will understand. This is north pole. This is the south pole. It is very close. Similarly, this is the south pole. This is the north pole. Correct? This is the north pole of the stator. So this will be the south pole. Please note that stator is fixed. It cannot move. The coils of magnetic field is rotating. Body, it is a body on which the field. So that means physically the stator cannot move. Body of the motor, it is bolted. The rotor is on a shaft with bearing, and because the magnetic pull created by these two winding, north and south pole, because opposite will attracts, the rotor will try to align, correct? It has to, this south pole should come here, because already north pole is fixed, south pole, so they get locked. Similarly, this north pole should come here. This will be considered, this will get locked. So that happens. So many degrees, the rotor will be pulled. So rotor is rotating. This how the pulling force is called torque. That is proportional to, we know that the torque is T equal to Fs multiplied by Fr multiplied by sine of alpha. Note down. Correct? This is the torque generated by the rotating magnetic field, which it interacts with the rotor magnetic field. Both, there are two magnets. One is a DC magnet, always the north and south pole, that is get locked with rotating magnetic field. Then as the field is rotating like this one, the rotor also, as long as power is available, the rotor will move like this. Rotor will move, get locked. Correct? The south pole always here, the north pole is here. Any given instant, this is the south pole, this is the north pole. So they get locked. So it is a continuous moving. For understanding only, we are given one instant. Now, the amount of the torque produced, I say TE, some books they put TM motor generator or TG, generated torque by the motor, like a DC motor, is proportional to in synchronous mode Fs, Fr multiplied by sine of lambda, where lambda is the angle, this angle. Okay. So now that means this field strength Fs and Fr is depends upon the core magnetic made because stator and rotor are made of magnetic material, laminated material, and also the air gap. The air gap plays very important. Please note that when I talked about mechatronics, I told that magnetic reluctance, correct? Magnetic reluctance also represented as R. In resistance also R, that is called DC resistance by any given material. Similarly, any material periodic table has a magnetic reluctance. What is a magnetic reluctance? If I take a square rod, solid rod, okay, made of aluminum, ferrous, nickel, or cobalt, correct? Or aluminum, any material similar to resistance, electrical resistance, or it has magnetic reluctance. The magnetic reluctance means opposition to the current flow. For example, if magnetic flux are coming, I have a bar magnet. I have a bar magnet which is north pole. This is a south pole. This side I have another bar magnet. This is north pole. This is south pole. That means you know that the magnetic flux created by this magnet will be attracted by the, sorry, this will be south pole, extremely sir. This is south pole, this is north pole. Okay, let me correct it. So this is south pole, this is north pole. That means not the magnetic field created by the left side magnet. I am showing green color, that is called magnetic field line. It is invisible. That goes getting attracted by this, it goes to the second magnet. But in between, I am putting another solid bar made of some material. And depending upon the magnetic R, correct? That is nothing but similar to electrical resistance. The opposing force generated, correct, by the material. This material. For example, I told you ferrous, it can be nickel, it can be aluminum. Any material in periodic table, I am talking about solid material. It can be gaseous also. Those material have magnetic reluctance. Magnet is how much opposition force this material generates for given square area, correct? Unit area, solid this one. So lesser the magnetic reluctance is better, correct? Magnetic reluctance R should be lesser for better magnetic flux flow. That means flux generated by this magnet should reach this magnet through this material. If magnetic reluctance of this material, what I am putting in between, if R is less, then more flux can go. It is like, for example, I have a wire, correct? I have a wire, solid square wire. I apply voltage, DC voltage. I am talking electrical. So this is voltage, this is current, I, correct? I equal to V by R. R is the resistance of the material. Already we know resistance equal to rho L by A. We have talked many times, correct? The cross-sectional area of this wire, length of the wire, and resistivity of the material. For the copper is different. So depending upon the resistance changes, then for the given voltage, how much current will go? What do you want? If more current has to flow from the battery through the material, the R should be less, correct? More current means we know I equal V by R. For a given voltage, for example, 10 volts, R 10 ohms means 1 amps. Instead that, if R equal to 10 by 5, 2 amps current, correct? So lesser resistance is better. Same thing only for magnetic material. Motor, all this thing work as basically work based on the principle of magnetism, repulsive, attractive force, and flux density. That depends on voltage applied, current flowing, and we say that. So the stator and rotor are made of magnetic material, iron plus nickel, some composition, cobalt, something, correct? This is called magnetic material. Ferrous is, we say ferrous plus few materials are magnetic, very good. That R is magnetic reluctance very less. That means more magnet can go, then more force can be generated. The force, the torque is proportional to Fs, Fr, sin lambda, correct? Sin lambda depends upon the phase lag. That we'll talk about later. Okay, so mainly it depends upon the field strength of the stator and field strength of rotor, magnetic field we are talking. So That means that depends upon, please note that the magnetic flux created by rotor will be flowing like this. Correct? It will flow inside the core and come back. It is generated by the rotor, and so the magnetic flux will go through this and come out and also interact with the stator winding, stator core also. Similarly, the magnetic flux created by this north and south pole of the stator, that also goes inside the rotor, comes, right? The magnetic flux goes and comes like this. So there are two magnetic fields, they are interacting. Correct? Magnetic flux created a stator, not only flows inside the stator core, flux is created by the coil because of current flow. Okay, because of Ampere law. That flux will automatically, being a both are magnetic material, rotor also magnetic material, stator also magnetic material. Only one small thing is, in between there's an air gap, because you know this is rotating, but the rotor should not touch the stator. If it touches, there's a friction. So there will be a gap. There's called air gap. The air gap, air is the reluctance, magnetic reluctance, air is very poor. Air is very poor compared to the stator and rotor, which is made of magnetic material. So that means for any given motor, any motor, whether AC motor, DC motor, the air gap should be smaller, but it should not be too small also, because they should not touch. Then the anyhow, in the actual this one, air will be passing through the gap to cool rotor and stator. Please know that rotor and stator, once current is flowing, there will be I square loss, which is also copper loss. Correct? So resistance of the coil, whether stator coil, rotor coil, multiplied by current flowing to that I square R, that much heat will be generated in rotor and this one. That should be there. But you know that end of the motor, if you see, there will be a fan. Because generally, for protection, they put a cowl so that you will not touch. But any bigger motor, smaller motor, will see a fan one side rotating, which is attached to rotor or armature in DC motor. So air will be sucked and flowing through this gap and cool the motor. Other side, you will see the hot air. If you run the motor long time with this one, so that means there should be a sufficient air gap for airflow also. Correct? But the air gap should be smaller. This gap, correct? Because it has high magnetic reluctance. That means the magnetic flux created by the north pole of the stator, it has to go to south pole through like this. It is flowing through this, through the rotor. Rotor is a magnetic, but it's stator, but in between air is support. That means small gap should be there. So the air gap also matters. So while designing motor, they will take care of that. Okay. So that's a work. Already we talked about it. What is a basic nature of synchronous motor? Today, just I wanted to complete a little more. Then we can start the what do you call as synchronous motor. We are continuing calculation. Torque produced by the motor. Some book they put TE, correct? TE equal to Fs, Fr multiplied by sine alpha. Already we know, sorry, sine lambda. I used this one. So it is sine lambda. Most of books are using that. Sine lambda. This is the angle between the, please refer the previous diagram. Okay. This diagram, this angle, correct? This is the Fr. This is the, Fs, this is Fr. Sorry, there are three things. I made a small mistake, extremely sorry. We are talking about, there are three vectors, right? Magnetic field vectors. One is Fs, that is this. This is the rotor. F small r, you can see that F small r rotor. Then, because there are two magnetic fields, there will be a resultant magnetic field, that is called, this is F capital R. Okay. Now, as I told you, that when you calculate the torque, this will be smaller, very small. Correct? Fs multiplied by Fr multiplied by sine of lambda. Already we know what that is. Okay. Now, if you wanted to write the final formula, correct? This can be still written as TE, can be written, note down, can be written as pi by 2, correct? It can be written as pi by 2 into p by 2 whole square multiplied by 5 r. I am using capital R. Please see here, this small r. It Fs multiplied by f small r into sine lambda. This can be again written like this. Phi r is the resultant magnetic field. Correct? I said capital this one resultant magnetic field, and Fr multiplied by sine into delta subscript r. So many Newton meter. Already we know the unit is Newton meter. Okay. So this can be written again. TE also can be written pi by 2 into p by 2 whole square into pi r Fr sine delta S also. So many Newton meter. Both are same, because if you see the figure, this figure, so this angle, so the total angle is called as lambda. The total angle between the stator magnetic field and the rotor magnetic field, this is called as lambda. The angle between the resultant magnetic field vector, this is Fr, correct? The middle one, this angle is called as delta S. And similarly, this between this rotor magnetic field, resultant magnetic field, delta R. Okay, so there are 3 angles are generally you will see in this figure. One is lambda, then delta R, delta S. Okay, so that is based on that you can write the final equation. You can use any one of the equation to compute the torque generated by the motor. Okay, that is one thing. Then next thing is, when we talk about this, the delta R is called as load angle, and delta S also called as load angle, because it is with respect to resultant angle. The load angle with respect to stator and the resultant magnetic field vector, or between rotor and resultant magnetic field. This also both are called as this one. So you can see that the two formula both are same, correct? Because of that, you can use any one of this. In one formula we are using delta S and another delta R. Okay, angle between the resultant magnetic field and the rotor, and angle between resultant and the stator winding. Otherwise, we can use Fr, Fs, Fr, that is rotor angle multiplied by sine alpha. This is called as load angle. Sorry, torque angle. Lambda is called a torque angle. Note down. This is what they use. Lambda is called a torque angle. If you are given torque angle value Fs and Fr, you can compute the torque of the synchronous motor using this formula. Instead of that, if you are given delta R or delta S, correct, and the Fr is there, phi R is there, now P is number of poles, pi is constant, all these things, then you can compute using this formula. Sometimes what they do is, this equation can be further written as minus pi by 8 into p square, correct? So p by 2 whole square is nothing but p square divided by 4. Denominator already there's a 2 into 4, 8. So that's why pi by 8 into p square into phi r Fr sine delta S, or you can substitute delta R. This also will give the final result. So in some books you will see TE equal to, you will see this. Not only formula, in the exam you can expect the pole values are given, Fr is given, correct? Magnetic fields, this one, Fr, Fs, all these things. Accordingly, you may need to calculate the torque produced by this one. P already know number of poles. Number of poles. And this already I told, correct? The phi r is the resultant magnetic field, Fr is this one, and pi is a constant, 8 is a constant, then automatically you can compute the motor. Okay. Now, before closing, I want to do this one. Generally, when we talk about motor, this kind of AC motor, all those things, there are two magnetic fields are working, the resultant magnet, how to compute. They say what you call a phasor diagram. To explain the motor working, torque generation, they use what you call a phasor diagram. Phasor diagram, for example, the stator magnetic field is done a Fs. It is shown in this one. Then my rotor magnetic field, this is my Fr. Okay. Then the resultant magnet is going to be like this. Okay. So generally, these two. Sorry, let me. So the resultant magnetic field is going to be a parallelogram. Okay. So this is our Fr. And as I told you, this angle is lambda. Okay. Is called as lambda is called a torque angle. Okay. Then the angle between this is called as delta R. Similarly, this is called as delta S. Correct? That is this one. Both are called as load angles. Load angle means you know that if you see the motor working, already we explained. Here, the rotor is connected to a load. Correct? Load because of there's inertia. Load has a mass because of there's inertia. So the rotor wanted to rotate along the rotor magnet. Correct? It is a magnet. Rotor also magnet. That magnet is locked with the stator magnet, and stator magnet is rotating. It is rotating magnetic field at synchronous speed. So it has to go. In that case, because of load, the stator cannot catch. Correct? So if I see that magnetic flux generated by north and south pole, this is the rotor. This is my stator. Correct? Stator in which there's a north pole. This is the south pole. And if you see here, correct, between these two, the magnetic flux generated is attracted by this. This should be south pole, this should be north pole. Okay, so this magnetic wanted to go and join, get attracted. That means the rotor realigns, trying to catch. This fellow is rotating. The both north and south pole is rotating stator at ns, and the rotor magnet you wanted to get locked with this, it has to align exactly like this. So, but you will see there's a small angle, correct? That's why this is called a load angle, correct? So, if you connect more load on the shaft, mass of the load become more, this angle delta R or delta S will be bigger, correct? So, that means to angle should be lesser, because the whole idea is the rotor should get locked, aligned with self-alignment, correct? North and south of this one, rotor, and should, this is north, this is the south of the stator, correct? This is stator. Perfect condition is like this, but it never happens. There'll be angle, load angle will be there. That depends on what is the load of this one. So if you try to give more load, what will happen is the torque produced by the magnetic flux TE equal to Fr Fs into sine lambda, correct? If this lambda become more and more because of more load, and the torque is generated not sufficient at one load condition, the synchronization between the rotor and stator will slip away. That means you are overloading your motor, correct? The torque produced is lesser than torque needed to drive this load. Correct. So that's why I said motor will synchronous motor will run at synchronous speed. If load become more, that means this angle is becoming more and more. The angle lambda is becoming more and more, or delta is become load angle, become more and more. What will happen is the torque produced is not sufficient by motor. The motor will stop. Correct. Suddenly stop but please see that your stator winding still you have the magnetic field. It creates. But the magnetic interaction, the torque generated by this formula is not sufficient to drive the load of the attached to the rotor. So it stops. That's why we say synchronous motor will run at synchronous speed, and it can take load such that when the generated torque is not sufficient for, I say, inertial torque, Ti, that depends upon mass, correct? Mass of the all this mass together going to have this one. Thus, the inertial load is more than the torque generator. Motor stops. We say that they call stalling torque. They say it is a stalling torque. Okay, so this is one thing.
Question I have.
Yeah, yes, please. Please.
Can I ask, sir?
Definitely.
Equation that you have written is, sir, equation that you have written is basically Fs into Fr multiplied by sine lambda, right, sir?
Yes, that is called torque angle.
And lambda is basically the load angle or torque angle, whatever you call it.
Lambda is divided by 2 because this load angle is different. This is called torque angle. Lambda is called torque angle. This is torque produced by the motor.
Sorry, torque angle. So torque angle.
It is torque angle. Load angle is delta.
Right, so my question is.
Yeah. Yeah, please.
Okay, sir. So my question is that, sir, when the fields are aligned completely, what I mean to say is when the stator is exactly in phase, like there is no.
Then this will be zero.
I would say
lambda will be zero. The torque will become zero. Motor will stop. Yeah, I understand where you are going. I understand. Correct. If the angle becomes zero, there's no torque produced.
Okay.
There is always because the magnetic stator magnetic field no mass. Rotor has a mass. Correct. Because always there will be angle. In no load condition also, this lambda torque angle will not be zero. Because rotor has some mass. That angle, because it cannot exactly align. Because this is trying to catch. That's why I told you to start the synchronous motor. You have to rotate the rotor physically. Because already is magnetized. Because you are given DC voltage, north and south pole is there. You rotate this one close to the NS, synchronous speed. Correct? Rotor will be rotated using external motor. So that at one stage, it will catch and align. But even once it catches, because of mass, you are removing the starting motor, rotor has the mass. Rotor mass, because of that, it will lag. The speed will reduce little bit. So never, I will say never this will become zero. If it become, motor will not be able to produce torque, no torque this one, correct? So there will be a little, rotor mass itself acts as a load in no load condition. In actual load condition, because of that, lambda will become more and more, correct? And so that with the divided by 2 is going to give the load angle, correct? Load angle resultant plus this one, that's what we are talking. Thank you for asking question, kind of it. Okay. So now that you know that, we know what is the formula. Fs we know, correct? And now I want to draw how the torque power and the speed curve. Generally, when we talk about motors, here x-axis will be speed, generally omega in radians per second, correct? Generally, angular velocity represents omega, correct? From this one, and now I want to draw what will be the speed torque curve for this. So one curve is called torque curve. For synchronous motor, the torque will be like this. Okay, this is the TE, torque generated by the rotor. After that, you have frictional torque, bearing torque, all those things going to consume. Resultant torque only going to drive the load. Okay, that we'll see. So then, as a synchronous speed, already we see that this speed is called as W base. Okay. And as you increase the load, correct? As you increase the load, the this one go on increasing, correct? So at one stage, load become more, then the motor will start, correct? That is called omega max. Okay. You can see that from 0 to V the omega W base, correct? W base, the speed torque remain constant, correct? I told you it can take load with up to the particular phase. Once it becomes the speed start dropping, correct? At particular load, then it will stop, correct? That is called W max. Okay, so the x-axis we are talking speed of the motor, right, in omega radians per second. Y-axis we are talking about the power and as well as the torque. Same axis we are drawing. If you see for synchronous motor, I have drawn the torque curve in violet color. If I see the power curve will something go like this. For synchronous motor, it will go. Okay, let me clear some part of this. Which is not need already you noted down. This is here. So this is power. This is torque T already I mentioned. Okay. This region from here. This region is called as constant torque region. You can see that it is a flat curve, correct? The violet color, it is a flat curve up to W base. From 0 to W base, it remains constant. Okay. After that, torque is start falling, but power remain constant. This area, I can say that up to the max, this area is called as constant power region. You know that power equal to NT, correct? So this region, torque is constant. This region, power is constant, but because of multiplication, this is how the speed torque curve of a typical synchronous motor. Okay. So speed torque curve already we saw. And one small thing we have to see before going to next type of induction motor. We know that we are applying, correct? We apply a terminal voltage to each coil, stator coil. Okay. So, and when you apply a terminal voltage, for example, I apply say 200 volts. For example, I'm saying, correct? Applied voltage, I'm talking 200 volts, which is fixed now, and the stator and stator winding, correct? The stator winding is a copper wire, and also stator winding resistance, correct? The stator winding resistance and leakage magnetic resistance. We are talking about stator resistance and magnetic leakage magnetic resistance are negligible. Then this is a condition when we apply a fixed voltage, and if the stator winding resistance and leakage resistance are negligible, very small value, then the terminal voltage can be written as, I can say it is capital V is nothing but √3 into 4.44 into kW into, because everywhere the multiplication factor is there, multiplied by F into phi R into NPH. Okay. these are since the root 3 comes, this is a three-phase motor, correct? Root 3 is a constant for three-phase motor, and 4.414 also is a constant. Kw is the motor related parameter. If these parameters are given, then you can find the terminal voltage. Okay. So now finally we can write T, torque generated by motor, into K into delta R. Correct. Delta R is nothing but, you know, the load angle, sine of delta R. Okay. Into K. K is called as motor constant. It is nothing but the K represent which terms you can we saw that the whole thing, correct? The whole thing is called as motor constant K, because it depends on pi by 2 into number of poles pi r. For given motor, the manufacturer may give the motor constant as synchronous motor, correct? Once that value is given, then you only thing what you noted, you need to know the delta R, correct? R, which is same as delta S. Multiply it by sine of delta K, you will get what is torque generated by motor. This how you calculate the synchronous motor torque. And phasor diagram we saw. And last diagram what I want to draw is speed, that is a torque versus speed curve. Torque
Sir,
0 to T max. Yes,
go to the
please.
previous slide, sir. We were not, sir, we are noting down. Please go to the previous slide, sir, please.
Yeah. I may try to scan and send my lecture notes if possible. But only thing is after the midsum exam. All the notes what I'm teaching, it said no, I'm taking, I will send all those things after the midsum. I'll send it to you so that you for your end-sum exam can prepare. Handwritten notes I have, from that only I'm teaching. Those things I will scan and send it to you after midsum exam. Because generally I give the answers, this kind of notes, important note if possible, when closed book exam, not for that is closed book and also invigilated. Don't think anything otherwise. Generally, that is why my policy. Because generally we try to give only during the corona time all those things, some important notes. I ask students to take the notes. Sometimes I try to share, but not full. This whatever available. Many this one I will try to share. Okay. So the curve is going to be torque is in the x-axis. Start from 0 to T max, motor maximum torque what it can produce. Then this is speed of the motor. The maximum speed it can reach is ns. You know that, correct? Motor can reach, synchronous motor, 0 to ns. This is the maximum. So it can go and it will maintain speed when the torque, load torque becomes more than the maximum torque, correct? This is the maximum torque. Correct? Then speed will become 0. You can see the suddenly it drops. Theoretically, speed is maintained constant for the 0 no load. This is no load condition of the motor to this is the maximum load condition T max. Up to that max load condition, the speed will remain constant. Even if you load as you are putting more load, the torque will be generated by motor. And once the torque reaches T max, after that, if you try to load, what will happen? More motor will start and the speed will become 0. That's what this represents. Okay. So where this is application of the synchronous motor. Okay. Main thing is wherever you want, wherever constant speed to be maintained, even when load is varying from no load to maximum load, correct? Constant speed drive is needed. Constant speed drive is needed. You will use synchronous motor. Another thing, it is used for what you call a power factor improvement. Power improvement, especially AC it is required. Okay, power factor improvement can be achieved using synchronous motor, correct? AC power factor. Okay, that is nothing but the power factor is nothing but I have a load, correct? I have a AC source to which I connected a load. Okay, this is my load. Load can be pure resistance, or it can be pure inductor, or it can be pure capacitor, or it can be combination of RL, RC, or RLC. Okay, the load can, that means it can be just a resistance alone, or it can be a coil, or it can be capacitor, or combination any three. Correct? I am applying AC voltage. Correct? When I apply AC voltage, there will be a current, AC current will go. I say IAC, VAC, and IAC equal to VAC divided by Z, where Z is called as impedance. Okay, how will you calculate Z? Z equal to root of R square plus X. Correct? So generally what you say, X is nothing but XL plus XC. XL is called inductive reactance, XC is called as capacitive reactance. So if this is the resistance, from that if you compute Z and substitute Z in the denominator, then there will be, you can find out RAC. Okay, IAC. Okay, once IAC, but problem is, if depending upon, that means I am applying the AC voltage, which is in a sinusoidal example, correct? Because generally we represent this my VAC. This is my time axis, T equal to 0. This is the amplitude plus V minus V. And how the current will be flowing through resistance load. If it is a pure resistance load, if load is a pure R only, the current will be like this. Okay, you can see that there's no phase angle. Voltage and both are aligned, but amplitude will say, this is my IAC, this is my VAC, correct? But you can see the shape also sinusoidal, and it is in phase. This is 0 to 180 degree, 180 to 360 degree. This is one cycle. You will say current and voltage are in phase. In the best case, if correct, it can amplitude will vary, correct, the difference, but they will in phase. If it is inductive, correct. So if it is a inductive, this one, this is my VAC. IAC, I say that inductive, right? Then what will happen is the current will be like this. Okay, so it will be. So now you see that there's a phase angle. This is called as phi, which is called as phase angle. Okay, this is for inductive load. Instead of that, if I have a capacitive load, okay, I have a capacitive load, my voltage is like this, my current will be flowing like this. So this is my IAC, this is my VAC. You can see that there's a phase angle, phi. Correct? This is called a lagging phase angle. This is called as leading phase angle. Inductive load, there will be a phase difference. Correct? Apart from amplitude difference, but if the resistive load, both will be in phase. Correct? And if you RLC circuit, depending upon R value, L value, C value, the Z changes. When the Z changes, automatically there will be a phase angle change also happens. There's a formula for that, we can, but that is so. But generally, if in AC this one, both should be in phase, voltage and current. That means there should be pure resistance, correct? The denominator should be pure resistive load. But motor, synchronous motor, it has a coil, so it has inductance. Coil is made of copper wire, it has resistance, so it is called as RL circuit. Even though it looks a simple coil, all motor here, armature coil, rotor coil, correct? Or stator coil, field coil, all are copper wires. But once you make as a straight wire is wound as a coil, it attains L, inductance comes. And because since it is made of some material, copper, aluminum, something coil, it has resistance also. So a coil cannot be considered pure inductance. Motor coil, it should be considered as RL circuit. Because of that, there will be a phase shift happens. Correct? If more phase shift happens, so what we call a reactive power. If phase angle phi becomes more, reactive power increases. Correct? So reactive power increases, that is not good. Correct? Active power only a measurable quantity, reactive power shouldn't. So how will you use this one? The phase angle should be reduced. So if you have an inductive load motor, what they do is, I have a coil which is represented by resistance together, and I add one capacitor. Correct? This is my actual load connected to AC power. Correct? A voltage is applied, IAC is flowing. Because of it, there's a phase angle, there's a reactive power comes into it. We say that VAC multiplied by IAC into cos theta, where theta is called as phase angle. Correct? So this is the power. PAC equal to VAC multiplied by IAC multiplied by cos theta. But in case of pure DC, P equal to V into I. This factor, cos theta business will not come. Where this is called as power factor. Cos of the theta is represented as power factor. You know that theta will vary 0 to 90 degree only. Correct? So if it's varying 0 to 90, cos value will vary 1 to 0. Correct? If the this cos theta becomes 0, that means the power is called pure reactive power. Correct? In motor, in case of pure resistance, the theta will be 0, cos 0 equal to 1. So it is that means if I connect a resistive load to a AC power, it works as a pure active power. The cos angle, this is called power factor. Power factor become 1. Cos theta equals this one. That's how it works. But in case of motor, the angle will not be 0. It can vary from 0 to 90. Because of that, there will be reactive power. The reactive power should be compensated. How will you compensate? You have to make theta equal to 0. What I do is, across motor, I add one capacitor. Correct? So you see your fan motor, all these things, there will be a small capacitor. Fair. It's a starting capacitor, they say. That is to reduce the phase angle. So the power factor improve. So synchronous motor can be used for making the theta equal to 0. Power factor angle should be 0. So in big factories, you have a lot of tube light, big factories, correct? So for example, plant, maybe hundreds of motors, correct? Then lights, tube lights, which are chokes. Then you have fans, correct? Circulate air in the factory. So that means lot of inductive motors are connected. In that case, power factor will become lesser and lesser. So to stop that, what they added, they put capacitor banks. Otherwise, they can put synchronous this one.
Please mind the gap. Pradeep, can you please mute your...
Pradeep, listen to this class. Don't listen to some other class parallel. You won't understand both. You are seeing some video or some lectures and just this one. This is not going to help you in your exam. Beyond that, I am not going to say anything. Okay. The last, this one what I want to say is, there are two types of synchronous motors. Note down. Synchronous motor, there are two types based on the type of the rotor. Okay. I already told you, rotor can be, I first draw the stator body, correct? In which you have coils, wires, three-phase wires, embedded. Three-phase AC, this is my stator. Correct? Stator coil, stator body is made of laminated core on which three-phase laminate, and you are supplying three-phase AC voltage. Then you have a rotor. We are seeing cross section of this one, in which again there are coils. I am saying just some 4 sets of coil. A coil is there everywhere, and current is entering like this. Since we are cut section, we are seeing current is entering and into the coil, and here it comes out. Okay. So what I will say that there's a since there are coil, there are two coil, both this is supplied with plus voltage. This is negative voltage. You know that rotor, we need to supply DC voltage, plus terminal connected this side, and the current goes inside coil, comes out minus side. Okay. Now, since you are supplying this, there is a rotating magnetic field rotating at NS, correct? In this direction. And we have the magnetic field, correct? Magnetic field, I say that stator south pole, stator north pole of stator. This is south pole of the rotating magnetic field. Same time, this is the north pole of the rotor. This is the south pole of the, south pole of the rotor. Okay, so you can see that already it get locked, correct? So it is rotating at this one. These two are south and north is attracted. So these two are attracted. So the rotor is rotating like this, because magnetic field rotating together, the rotor also rotating. Okay, you can see that here this is a cylindrical shaped rotor, correct? No projection. It is a smooth cylindrical shape in which there are grooves. Please note that these are grooves. I am saying only 4 grooves. The coil, the shape of the cylinder is a circular in shape, solid lamination, in which grooves are there, in which we are embedding the coil. This is rotor coil. If the rotor is like this is called as non-salient pole type synchronous motor. Okay, other than this one. Instead of that, what I can do, the other one is called salient pole type motor. Okay, so circular in shape, but there are projections. Okay, so many times they show like this. Coil will be wound over this. Okay, so since this is called pole pieces, correct? Please note that previous also non-salient, there are poles were there. Poles are created by the current flowing through the coil of the rotor, but it was cylindrical shape, no projection, in which there are grooves in which the rotor coils are embedded. Okay, in this case, you can see that this is a cylindrical, this one, but there are projections, correct? And coil is there. This type of rotor is called as salient pole type. Poles are projecting a cylindrical shape. From that, there's a projection, correct? So this is called as the salient pole. And both type of motors are available, correct? They have some advantage, also disadvantage. I think time already up. Maybe I close this. Maybe just another few minutes. I will close it. So both type of motor, synchronous motors are available. Salient type, in which the rotor poles are projecting outside and which coils are there. But of course, the main part is a solid cylindrical shape. But of course, there's a projection. This is called salient pole. Other one is this rotor will be no projections, cylindrical solid, this one with grooves, and that is called a non-salient pole. There are some advantage between both. Okay, I will draw what is advantage. One is called non-salient pole, note down. Pole type, other called salient pole type. First thing is the rotor diameter. It has this non-salient pole, the rotor diameter, smaller rotor diameter. What I'm saying is, generally it will be in cylindrical shape, right? So this is the shaft coming out. There's a bearing, right? Here there are grooves, right? The rotor has some length and it has some diameter also. It has some diameter, it has some length, correct? So the non-salient pole motor, no projections, and it will be smaller. The diameter D will be smaller for the same power, same torque compared to salient pole type. Non-salient pole, the diameter will be small, but length will be longer. The rotor length will be longer. So smaller length and longer, smaller diameter, longer length. Okay. Then since the gap, correct? There's a uniform air gap, correct? I told you this is my rotor, this is my stator. Sorry, there's a gap in between, correct? There's a because this is in cylindrical shape. Pure this one, there's a uniform gap, so air will be sucked in. Correct? I told there'll be a fan attached to this, and it will suck the air to cool the motor. Air will be going like this in the gap. So since there's no projection, both the stator and rotor are cylindrical with a gap, the windage losses. Because air sucked in, correct? Air is sucked in by the fan and comes out, correct? That is going to smooth the gap and cooling this one. So windage losses will be less because no projection. We're going to create turbulent airflow. Windage losses will be less. Okay. Then it is a robust construction, correct? Please note that it is a robust construction because solid cylinder with grooves only, no extra projections. So when the rotor rotates at 2000 RPM, 3000 RPM, the forces created, centrifugal force created will not have any effect, correct? It is a highly balanced. So robust construction without any projection. So it can run at high speed, correct? Non-salient pole synchronous motor generally 3000, 5000, 6000. But please note the speed. NS equal to 120 F divided by small p, correct? So you can give higher frequency, so to attain higher speed, 3000 RPM, 5000 RPM per given number of pole, correct? So 120 is a constant. If I vary the input supply frequency, I can go to any speed. For given supply frequency, for given a constant speed, it maintains, correct? So since there's no projections and robust construction, high speed operation is possible. High speed operation is possible compared to salient pole because there's a projection. Okay, then the last one is because uniform air gap is there. Due to uniform air gap, correct? Flux, correct? Distribution will be uniform. Because of that, it will be uniform. So torque production will be smooth torque projection. For one because rotor is going to rotate, no, as it rotates, the torque is going to be smooth torque production or uniform torque production at any given angle because there is no projection. Okay. Then, as I told that it has high speed operation is possible, correct? High speed operations generally high speed synchronous motor. Synchronous motor is running high speed means generally it will be a non-salient pole. High speed operation. Okay, because you know that because it can withstand higher centrifugal force. Because you know rotating object producer, since there's no projection, it is a solid uniform shape, it can withstand. So high speed operation for that, if you want to, you have to go for non-salient pole type only. And again, last one is well balanced. Mass balance. So that the being a cylindrical shape, correct? It is well balanced and no vibrations, minimal vibrations. I can say minimal vibrations. Okay, this is the advantage of non-salient pole type. Okay, so what about this one? Salient type. Salient type, better ventilation. Because you are supposed to give, because there are projections. I told you, I have the rotor, there are projections. And this is my stator. Correct? Because of projection, large from this one, large gap will be there. This is air gap, correct? So that means more air can go. Better ventilation is possible. Cooling will be better in salient type. And of course, it has a drawback. It will be a larger diameter. Right? The motor size will be larger because the poles are this one. Then third one is the fold paces. What I call this is my fold face, correct? The projection they call as fold paces, correct? Will be shaped. Face will be shaped such that the magnetic flux is uniformly distributed. Okay. Generally used for low speed operation. Because as I told you, poles are projecting. If you run higher speed, it will experience a lot of centrifugal force. The pole pieces can create a lot of centrifugal force. It can, when go higher speed, the motor can break. So low speed, generally they recommend low speed operation. In order to avoid higher centrifugal force created by the projected the pole pieces. Okay. Generally, they go up to, generally can be more 1000 to 1500 RPM only, generally. Around 0 to 1000, that is max speed you will go. Salient pole, correct? Non-salient pole can be even very high. 3000, 5000 also it is possible. And not well balanced. And at higher speed, there can be vibrations. These are the important points of the two type of servo, this one, the synchronous motor used. I stop here. Tomorrow we will start about the most widely still used is what you call induction motor. Induction motors are very rugged. It is another type of AC motor, and it has a lot of advantage because it is used in electric vehicle, agriculture, industry, wherever you want constant speed motors and AC motor with a rugged construction, correct, with minimal maintenance, and they'll go for induction motor compared to synchronous motor. So we'll see that in next two classes. Then we will talk about power electronic circuit later. Okay. Any questions? No more means please give your attendance before leaving. See you tomorrow by 6 o'clock.
Thank you, sir.
Thank you.
Okay,
Take
thank
care.
you, thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.
Thank you. Take care.